All right. All right. This is day 3 on factoring. See if I can get this out of the way. Okay, and if you think about what we've done so far, day 1, we've practiced doing the GCF. In fact, we've done GCF every single day because you always have to do that first, no matter what the polynomial is. Sometimes there is a greatest common factor, sometimes there isn't, but you always need to look first. Then also on day 1, we practiced factoring quadratic equations. We'd GCF them. It'd be a quadratic, 3 terms in it most of the time, and we could use that RS method to factor it. Then yesterday, we looked at GCF again, and then we factored trinomials that had an a that was different than 1. Okay, a was not equal to 1. It was 2, 3, 4, 5, or -2, -3, -4, etc. And we learned we had to multiply the a times the c together and then find the r and the s values. Now today we're going to look at what are called the special cases. Okay, and we got the difference of squares, difference of cubes, and sum of cubes. And when you see these, they're going to be rather intimidating looking, but don't panic or anything. We'll work through many examples and make sure we can all handle it. So let's take a look first. So on this slide, we've got the 3 different special formulas. You can see up here that all of these have 2 terms in them. Oops. Okay. The first one is called the difference of 2 things that are squared, or the difference of squareds, we abbreviate it. The difference is because it's going to be a subtraction problem. It will be something squared, and we call it difference because subtraction is the same thing as find the difference between 2 things. So they call it the difference of squares. And so you can see it's 2 things that are squared, and they are subtracted. And you just figure out what they squared and do an a minus b, and what they squared and do an a plus b. That's our easy one. Okay, the tougher ones, we got a difference again. So it's a subtraction, but this time it's going to be cubed things. And so you can see it's something cubed minus, that's the difference part, something cubed. And man, look at the size of that factorization. It can be really easy though once we memorize that. And then lastly, we got a sum. Okay, so it's going to be an addition of 2 things, and they're both cubed. And so you can see that sum right there. The addition of 2 things that are cubed, and again, we get a long factorization. I do want you to notice these 2 are very, very similar right here. And we'll look and see if we can figure out some patterns to help us with all 3 of these things. So the next slide, I've got a few. This slide really tries to highlight some of the similarities and differences between all of these formulas. So the ones that have reds on them, okay, the red indicates it's a difference, okay, and I've highlighted the spot in the original formula, okay, so this is an a squared minus b squared, difference of 2 squareds, and this is an a cubed minus b cubed. But what I want you to look at is the formulas over here. In the a squared minus b squared, there's only 1 minus sign. And the difference of cubes rather, it starts exactly the same way with 1 minus sign right there, the first one, a minus b, there's no difference. And then the rest are all positive. Okay, so this one only, the first one, difference of squares, gets 1 minus sign. Difference of cubes gets 1 minus sign. You use it right away. The sum of cubes starts with a sum. Okay, just like the minuses start with minus, the sum starts with a sum. And then comes its minus sign. All of these only get 1 subtraction sign in them. Okay, so as soon as you've used it, especially in the difference of squares and difference of cubes, you use it right away when you do a minus b. Everything else is positive. And so you'll know that you've used it up. In the sum one, you go plus, and then you have to use your minus sign. And once you've used it, you're done, and the last one is positive. So let's look at some other patterns. They all start with this A-B combination, A and B, and they just follow their sign. So you start with it's a difference, so you start with the difference. A difference, you start with the difference. A sum, you start with the sum. Okay? Then in our trinomials here, look at how similar they are. A squared, A times B, and B squared. They're identical to each other. Okay? Except for this sign right here. These first two signs just get flip-flopped. And so going forward, hopefully you can kind of memorize these things based on these patterns. Hope that'll help you memorize them. And now let's go on to some examples. All right, let's start with the simplest one, the difference of two squares. Difference of two squares, it's got to be something squared minus something squared. It's got to have that minus sign in the middle. And it's just going to be A minus B, and then A plus B. So you just got to figure out what they squared in each case. Essentially what you're doing is just kind of mentally square rooting these. This is like an x that's been squared, and this is a 2 that's been squared. I'm going to write this off to the side so I can line things up a little bit. So this is like an x that's been squared minus a b, the 2 that's been squared. And so whatever's been squared is your a here, and whatever's been squared there, your b, is a 2 in this case. So a is x, b is 2. And so when I write this out, I just have to, where I see an a, I put the x. Where I see a b, I put a 2. Where I see an a, I put an x. Where I see a b, I put a 2. And I'm done. And you can see as I test this out what happens as I distribute it. You get x squared plus 2x. And then when you distribute the negative 2, you get negative 2x minus 4. And so this stuff will always cancel out in a difference of squares. And that's why it only has those two terms in it. Real simple the difference of squares is. Okay, we just have to recognize squares. So you may want to have a list of some of your perfect squares. So I'll make a list for you here real quick. 1 squared, 1, 2 squared, 4, 3 squared, 9, 4 squared. So we're looking for things like 16, things like 25 is a perfect square, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is terrible 9 is 81, 10 squared is 100, 11 squared is 121. I apologize for my dog, hold on. 12 squared would be 144. Okay, so we could go on and on. So let's go ahead and try this next problem. Okay, we got 9 and 16, and we can see that 9 and 16 are both in our list here. So they are perfect squares. So what we want to think of this as is, what do you square to get a 9? Well, it's a 3. And we want an x squared, so it's got to be a 3x that's squared minus a 4 that is squared. So there's our a. A in this case is 3x, and our b is that 4. And so we just go a minus b, it just follows the sign, and then the other one we've used up our negative has to be a positive. 3x minus 4, 3x minus 4, and 3x plus 4. Sorry about that. They're going to look almost identical except for that one sign is going to be different between the two. The next one, we got to be careful here because we haven't had to do this yet. But don't forget step number 1 is always GCF, and these are both 25, so we could pull a 25 out of that, giving us this quadratic x squared minus 1. So the question is, it's got two terms. Is it a difference of squares? And that's the only one we're looking at because it's an x squared. Well, 1 squared is a perfect square. I mean, 1 times 1 is 1. So we're going to think of this as 25 times, and this is like an x that's been squared minus a 1 that's been squared. So a is x and b is 1. And so my final answer is my GCF, a minus b, a plus b. And we're done. And then our very last one, kind of a trick question here. Maybe a little bit careful, okay? certainly a perfect square, but it's a sum. This would be called a sum of two squares, and we cannot factor those. We do not have a formula for them. Sums of two squares are always prime. So don't waste your time trying to factor it. Okay? It's got to be a minus sign, and they've got to be perfect squares. And let me illustrate one here real quick. Let's say you got x squared minus 6. Again, kind of looks like a difference of squares, but 6 is not a perfect square. I can't square root of 6. 2 squared is 4, 3 squared is 9. I don't know what squared gives me 6. And therefore, this one would be prime. Okay? It's got to be perfect squares in order to use the difference of squares. In practice, if I had something like 36x squared minus 9, I don't have to write down what a and b are. I just square root them mentally in my head. Square root of 36 is 6. So that's a 6x, and the square root of 9 is 3. 6x minus 3 and 6x plus 3, and I just broke rule number 1. See if you can figure out what it is. I forgot my GCF first. Everybody's divisible by 9. I should have done 4x squared minus 1. And then square root of 4 is 2, so it's 2x minus 1, the square root of 1, and 2x plus 1. And I noticed that I had forgotten to do that because if I look at each of these factors, there's a 3 that can come out of both of these, giving me 2x minus 1. There's a 3 that can come out of both of these, giving me 2x plus 1. And then the 3 times 3 is this 9 right there. So I could end up at the same spot, but it's clearly much easier to take out the GCF first. And once you take out the GCF, you'll have smaller numbers that you can square root. And so it'll be easier to figure out what a and b are. Okay, so that's the easy one. Let's look at one of these hard ones now. All right, we're doing a difference, so we know we got a minus sign between them. So let's kind of check these. That's a minus, that's a minus, that's a minus, that's a minus. So we don't have to worry about them trying to trick us here, at least not in terms of that. Now we got to figure out what they cubed. So what you have to do is go what times what times what? 3 of the same number. Let me throw my video in as I animate myself. And so as we start to attack these problems, we got to again make sure that we got the difference. All right. And then we just got to figure out what a and b are. So what did they cube? Well, x cubed minus 8 can be thought of as an x that's cubed. And then 8 is 2 times 2 times 2. So this is my a, and 2 is my b. And I'm going to line it right up underneath the equation. Wherever I see an a, I'm going to put an x. Wherever I see a b, I put a 2. Then it says take your a and put in an x and square it. Then it says take a times b. Well, a is x and b is 2, so it's x times 2 or 2 times x. And then be careful here. You kind of want to do this last one in your head. It says take your b and you square it. Okay? That means take b, which is 2, and square it. So it's really a 4 that you just want to stick in here, like that. Okay, so b squared, that is actually equal to a 4. Don't leave it as a 2 squared. That's just kind of sloppy at that point. Okay, and we're done. Okay, let's look at this next one now. Next one's a little bit tricky, and I'll explain why. We've got a minus sign, so it's a difference. Now, is it a difference of squares or a difference of cubes? Right away, we notice that 3. So if it's anything, it's got to be a difference of cubes. So that's an x cubed minus a, what can I cube to get a 5? And the answer is nothing. Okay, 1 cubed is 1 times 1 times 1, which is just 1. 2 cubed is 2 times 2, 4 times 2, 8. I skip right over 5. There's no way to get a 5. So this is not a difference of cubes. Therefore, I cannot use the formula. Therefore, I just write down this thing is prime, not factorable. And in fact, you guys, if you memorize some of your perfect cubes, you can tell pretty quickly if it's possible or not. So here's a list of perfect cubes. if it's a 1 and it's cubed, it'll still be 1. Okay, a 2 cubed is 8. So if you see an 8, that's a 2 cubed. 3 cubed is 27, so that's a perfect cube. 4 cubed is 64, that's a perfect cube. 5 cubed is 125, and that's about as high as we go. We could go up to 6 cubed, which I think is like 216. But nobody really memorizes. Some people memorize past 5, but most don't. I suppose there might be some special ones, like 10 cubed, be 1,000, right? 10 times 10 is 100, times 10 is 1,000. So that's kind of a special one. But really, it's going to have to be a number from that group right there. I'm trying to just grab him, but it's not going to let me. So I'm going to erase that list, and if we have to generate it again, we can. Spend a little time looking at those numbers and trying to memorize some perfect cubes. Let's look at this number. There we go, the third one on here. All right, we certainly have a difference. Right there, we can tell. Now do we have two perfect cubes? If you remember that list I just showed you, 27 was on it. 27 was a 3 cubed. And 64 was on it. 64 was a 4 cubed. 4 times 4 is 16, times 4 is 64. So we want to think of this as a 3x, because that's what the cube root of 27 is. It's a 3 that's been cubed. Okay, so 3 cubed is 27, so it's equivalent, minus, and 64 is a 4 that's cubed. That's my a right here. A is 3x. And this is my b. b is 4. Now we don't have the formula there, so let's see if we can remember how to write that. It starts just like difference of squares, a minus b. Then you square the first term, a squared. Then you multiply the ab. It's got to be a plus sign. We've already used up our minus. And then you square the b. So we have some symmetry there in terms of this is the a, first letter in the alphabet, and then this b next. Okay, but they're both squared on the front end and the back end. And in the middle, they combine, a times b. So let's see if we can write it now. Where there's an a, I put a 3x. Now I'm going to show you this really formal. Okay, I have to square all of a, so it actually looks like this. A is 3x. I got to square that. Then it's plus a times b, which is 4. Then it's plus, and the b is a 4, and I got to square it. So every time I substitute it, I essentially put it in parentheses. In fact, let's put these in parentheses. And now we can simplify each of those little terms. My first term is 3x times 3x. That's what it means to square it. So that's 9, 3 times 3, and x times x. So this is a 9x squared. This is just all multiplication. 3 times x times 4. We do the 3 times 4 times x. And then I square the 4. 4 squared is 16. And I forgot, I got so excited, I forgot my a minus b at the very beginning. Let's squeeze him back in here. Can't believe I did that. Got my dog playing out in the hallway. So I do have to have out front here my a minus b. So my 3x minus 4. X minus 4. Just like that. So this is my complete factorization. Okay. I forgot to mention it up here in number 1. I'll mention it now. This trinomial here in the difference of cubes is always prime. So we never try to factor him because that is just a fact of this problem. That thing is always prime, so you just stop right there. We cannot go any further. Let's look at our last one. Let's get rid of some of this if we can. Get rid of this junk over here. There we go. All right, so here's our problem. We got 8x cubed minus 8. All right, let's go through all our progressions now. The first thing we have to do is, if you remember, always check for a GCF. This one has one, both of these are divisible by 8. They also happen to be perfect cubes, but that does not matter. We're going to take that GCF out first. Then we're going to see if we have a difference, which we do, right there. We certainly have a cubed here. Well, is 1 on our list of perfect cubes? And it actually is. Okay, this is actually an x that's cubed minus a 1 that's cubed. Okay, because 1 times 1 times 1 is still 1. 1 is a perfect cube. It's a perfect fourth power, perfect fifth power, because everything 1 times itself is always 1. So once we've made this decision, it's just a case of remembering this is a now x, and b is 1. Let's see if we can do it without writing down our formula. So we've got our 8 sitting out front. Then the formula, and I'll write it above it, is a minus b. So we go x minus 1. Then it says take the a and square it. Okay, so we square the first thing we wrote down, the x. Then it says take your a and your b and multiply them. X times 1 or 1 times x is just x. Then it says take your b, which is 1, and square 1. Okay, that's our ab, and then we have to do our b, our 1, and square it. Well, 1 squared is just 1 still. And there is our complete factorization. And we're done. Okay, again, this is always prime over here, so we never try to factor it. It'll always be prime. Okay, let's look at now the sum of cubes. Even if you're a little lost on the difference, the sum of cubes is almost identical to it, except it has a different sign at the beginning. Sum of cubes starts with a plus b, then it has a minus. Okay, otherwise it's identical. All right, now we are looking at perfect cubes that are added together, the sum of two cubes, and it's almost identical to the difference of two cubes. Remember, the difference has a minus, and so it starts with a minus b. This is a addition, so it starts with a plus b. And then we only get to use one minus sign, so the next time you write down a sign, it's right there. It's going to be your one subtraction that you get to use in the problem, and then it's plus your b squared. Okay, so it's almost identical. The only difference is the signs and where they go. They both only have one minus sign. A minus b or a cubed minus b, you use it up right away. A cubed plus b, you use it as the second sign. And so we do exactly what we just did. This is an x. Let's write it to the side here so we can line things up. This is an x that's been cubed, and this is a 2 that's been cubed. 2 times 2 times 2 is 8. Where there's an a, I put an x. Where there's a b, I put a 2. Where there's an a, I put an x. Where there's an a, I put an x, and a b, I put a 2. So it's x times 2 right there, or 2x. And then again, we do this last one. Notice I used up my minus sign right there. And then when we do this last one, remember I talked about trying to do that in your head. You take the b value and you square it. So our b is 2, and we square that, and we just put a 4 right there. And our problem is complete. Not a whole lot of math involved. Just a lot of substituting and maybe once in a while squaring some stuff. Let's see if I can figure out which one's the eraser here. There we go. All right, let's look at the next one. We got an x cubed plus 1. Certainly a sum. Are these perfect cubes? If you remember our perfect cube list that I had, 1 cubed is 1, 2 cubed is 8, 3 cubed, 27. So these are the ones we're looking for. 4 cubed, 64, and 5 cubed, 125. If it's not one of those, we got a problem. Okay, but we do have an x cubed, and 1 is on our list. It's a 1 cubed. So we're going to think of this as my a is x, and my b is a 1 that's been cubed. 1 times 1 times 1. And then it's not a minus b I start with because it's a positive. In addition, I start with a plus b, x plus 1. Then it says take the a value and square it. So take the x and square it. Okay, then it says put a minus sign. Take a times b, x times 1 or 1 times x, and then add on whatever b is and square it. So 1 squared is still just 1. and that would be the factorization. Again, these trinomials, the one above and the one below, these guys are both always prime, so we don't ever waste time trying to factor those. Not possible. Let's look at the third one here. Kind of get him out of the way, but keep our list of cubes there. Okay, so we've got ourselves a 27. 27's in our list. It's a 3 that's cubed, so we can do him. And we've got ourselves an 8, and 8's in our list, and 8 is a 2 cubed. So we're going to think of this guy as a 27. It is a 3 cubed, and we got to get the x in there because that also gets cubed. And then the 8 is a 2 cubed. So our a is this whole thing, 3x, and our b is that 2. A is 3x, b is 2, and we start our substitution. A plus b, 3x plus 2. Now be careful, I've got to square a. Now a is 3x, and I got to square that. So I have to do the 3 times 3 and the x times x, which is 9x squared. Then comes my minus sign. I always have to put that sign there. It's always going to be a minus sign. And then I have to just take the a times b, and what I do is I just kind of mentally look right here, and in my head I go, well, what's 3x times 2? That's 6x. Let's give myself a little more room here. Our last thing we do is we say plus, so I write a plus sign. There we go. And I have to take my b term, my b is a 2, and I got to square it because the formula says take b and square it. That's 4. And I'm done. Not too bad at all. Let's look at the very last one now. The last one I'm a little suspicious of. They haven't tried to trick us yet. Let's see what we got here. Let's see. I certainly see a GCF because these are both even. They are both divisible by 2. So it's 27x to the 4th. 27 is a perfect cube. And 16 divided by 2 is 8, and 8's a perfect cubed. The problem is, this is an x to the 4th problem. I don't have any formulas for x to the 4th, so I can't use my sum of cubes, certainly not my difference of cubes or my difference of squares, because it doesn't have a minus sign. I can't do anything else with it. So we'd be done when we write just 2 times 27x to the 4th plus 8. Okay, now had it been, I take out the 2, and it was really just an x cubed plus 8. Then I could go to town on this. A would be a 3x, and b would be a 2. And then there's my a, there's my b, and I could factor it if it was cubed, but that's not the case, so I get to stop right there. And that should take care of everything. Okay, I'd spend a little time